Perfectly. So, hello from my side as well. So yeah, my name is Henriette Triebke and I'm a research engineer at Robert Bosch. And at the same time, I'm currently writing my PhD thesis at the KIT in Karlsruhe under the supervision of Professor Fortisch. So today's talk is about the calibration of spatio-temporal network states in microscopic traffic simulation. And actually, it makes part of sequential MATSim SUMO tool coupling, which is my topic of the PhD thesis as well. So, okay, I just like to jump right to the motivation. Why do we actually need another calibration approach? I guess there are already tons of it. So, but it depends, right? So depending on the use case you have with your traffic simulation, you need to adapt the calibration technique as well. So MATSim, Bosch demanded for like 24-hour drive cycles for shared autonomous electric vehicle fleets or for DAT vehicles. So they need it for vehicle prototyping and for requirement engineering in order to size the vehicle components correctly. And as I've been showing last year on the SUMO user conference, to do a sequential MATSim SUMO tool coupling is an appropriated mean to deduce those kind of drive cycles from traffic simulation. But I have to say that actually there's a major obstacle, and it is that SUMO cannot accommodate all the travel demand, which is prompted from MATSim. This has actually several reasons. One of the main reasons is that both transport or traffic simulation frameworks differ considerably in traffic dynamics and as well in network representation. And Bosch made it a further condition that the toolchain need to be run in an automated fashion. So I have no option here to clean all the network folds in SUMO manually. So I just have to deal with it that SUMO runs on an imperfect network. And this, of course, leads to congestion as well. So what can I actually do to solve this problem, to maximize kind of the network throughput in SUMO? Right, I have several options. Well, I could cleanse the SUMO network, but this is no option. This takes too much resources. But I could also detect the vehicle delays and spot the congestion and try to relieve it somehow. Or another possibility would be just to question the realism of the travel demand forwarded by from the MATSim side. And then, as the network representation in SUMO is different than in MATLAB, in MATSim, so the network resistances are different as well. So it would be only fair enough that SUMO can determine its own user equilibrium. And possibility number 5 would be, okay, perhaps I do not need to transfer 100% the travel demand from MATSim to SUMO, but perhaps just stick to an 80% SUMO travel demand, because for me it's only important that my eco vehicles, so my shared autonomous electric vehicle fleets, are similarly delayed in SUMO than in the travel time calibrated MATSim model. And option number 6 is, well, to create a synthetic ambient traffic. But as I've already mentioned, option number one is no real option for me. And option number 6, I actually do not need, because those options here serve my purpose quite fine. Okay, So here, a general outline of my presentation. So next, I'm going to talk about my methodological approach. So I'm going to talk about the global calibration technique and the local calibration technique. And I'm going to outline my test case. Before starting with the status quo, and the status quo means how much of the travel demand runs actually smoothly through the SUMO network up to now. And to give you an answer to this question, well, actually it's not a lot, so I need to identify more relevant parameter levels in MATSim and in SUMO in order to maximize the throughput in SUMO. In order to align both traffic states in both frameworks, I implement a genetic algorithm next. And in the end, the best fit solution is discussed. Okay, so actually the calibration technique I propose in this contribution is like a two-step technique. So I start with a global calibration approach by doing a network-wide fitting of the relative mean speed on all active edges over the course of 24 hours in MATSim and in SUMO. And I'm doing it by altering different travel demand, routing-based and hotspot relaxing measures by means of a genetic algorithm. And in this presentation, I'm going to talk only about the global calibration technique. The local calibration technique, which follows after, is a little bit different. It is spatially really resolved and not means-based. So for instance, let's assume that's a network from a bird's perspective, and all the yellowish areas, those have actually the same relative mean speed as in the global calibration for this time bin. And where the area is shaded in red or in green, I actually have to speed up or further delay my ego vehicles by adding or removing further ambient traffic. So yeah, that's the main difference. Okay, let's jump to my test case. It is of medium size. I indicated here the number of MATSim links and SUMO edges. And it is situated in Berlin inner city. And well, it's situated around the Brandenburger Tor. And to give you an idea how many agents I dealt with over 24 hours, well, it's 500,000 trips during 24 hours. And on the bottom, I illustrated some trip characteristics of a chosen ego vehicle. Those I need later on for benchmarking reasons. Okay, so let's start with the status quo. What travel demand share goes currently through the SUMO network? And to give you the answer right away, currently I'm only able to get 40% of the travel demand from MATSim through the SUMO network with SUMO default settings and with a new user equilibrium. So what you see here on the main panel is the relative mean speed on all active edges averaged over 24 hours and for 50 dual iterations for different MATSim travel demand shares. And whereas the relative mean speed here is averaged for 24 hours, you can see here in the sub-panels the relative mean speed over the course of the day. So representing different traffic states. So for example, I have free flow driving conditions here in D, and moderate congestion here in A and E, and B and C here, well, they are strongly congested. Sorry. And as you can see clearly, I'm only able to get 40% of the travel demand through the network without running into severe congestion here. And another thing is that the dual iteration procedure is not really stable, but well, it scatters a lot. And that is not what I want. So the next question is now, how could I possibly improve that? To do so, I do a parameter exploration next in both SUMO and in MATSim. And this leads me to this slide. So I have 3 scenario families. So scenario A and C, they concern SUMO, whereas the scenario family concerns MATSim. So what I need to do is that I will play here a little bit more with the teleport functionality or with the maximum depart delay functionality in order to relax the hotspots in SUMO right away. And here, as finding a new user equilibrium didn't work for me, I'm just going to allow for rerouting by playing with the rerouting probability and the rerouting period, and to prevent U-turns at a trip's end and at a trip's start, I just switch on the remove loops functionality. The scenario family B is more on the MATSim side. So instead of using a 1% sample share scenario in MATSim, I'm going to increase it to 10% because the 10% simulation shows less artifacts and makes the travel demand more digestible for SUMO. Another thing is that I'm going to reduce the inner city link capacity and velocity in MATSim, because the urban capacities in MATSim, they're actually too high. So what I do now is I'm going to reduce the velocities and the capacities on urban links in MATSim. And that helps SUMO a lot to accommodate the travel demand. So in total, I have more than 1,000 SUMO simulations over 24 hours with 500,000 agents. And actually, I do every parameter setting, each simulation with 30 different seeds in order to see whether the parameter is really robust to stochastic effects. And then each parameter setting is evaluated by a score. So those settings that lead to high relative mean speeds, they get a high score, or they those parameter settings that converge over the 30 seed trials that converge pretty fast and have only a small min-max range. And last but not least, if the number of teleported cars or not inserted cars is low, then this will result in a high score as well. Okay, due to time constraints, I guess I cannot dwell on this slide so long, but those are the results for the different individual levers. So I just want to say here that, so in general, it's a box plot illustration, right, of the results. And I just want to say that the scenario family A1, A2, and C3 have the greatest impact to maximize the throughput in SUMO. And the best scored levers I highlighted in the greenish area. And actually, it proved beneficial if once I spotted hotspots in SUMO where congestion arose a little bit. It proved beneficial to teleport the vehicles faster, or to not insert new vehicles there, because this prevented severe congestion on the long run. And by this, I ended up with less teleported cars and with less cars that could not be inserted. So this is only the impact of the individual measures, but what throughput in SUMO could I attain when I combine those measures? And this leads me to this slide. So to remember, before with the dynamic user assignment, I was only able to get 40% of the MATSim travel demand through the network. And even a travel demand share of 50% led to relative mean speeds of 0.35. Yeah, this would be here. And now with combining all the levers, actually, I increased my relative mean speed by 100%. So I'm now here. And I also compared the different MATSim simulation functionalities. And here I just want to say yes, it proved beneficial to do a MATSim 10% simulation trial and then to forward this demand to SUMO, and not only to take a MATSim 1% simulation trial. And it proved also beneficial to reduce the network capacities and link velocities in MATSim. This led to a better network throughput in SUMO as well. So this takes me to my final point, because I'm actually not interested in maximizing the SUMO throughput, but I want to align it to the traffic state I observe in MATSim simulation. And for this, I implemented a genetic algorithm in MATLAB. And this solves optimization problems by laws of natural selection. So I start here with the initial population with possible solution candidates, and each solution candidate here has kind of a has a set of 3 different genomes, and those genomes correspond to different SUMO settings. And with this, I'm starting a SUMO simulation for each possible solution candidate. And I analyze the SUMO simulation, and in the end, I calculate the relative mean speed in order to evaluate the fitness of the possible solution. And in general, I try to minimize the error and daily relative mean speed on all active edges in a 50-minute interval. And based on those results, new generations are formed by altering the genomes of the parents by natural laws of selection, crossover, and mutation. Which brings me actually to my last slide. Oh, not last, but nearly last slide. So this is the best fit solution the genetic algorithm found. And here is the result of the global calibration technique. So as you can see right away, the genetic algorithm aligns pretty well the travel times or the traffic times during peak hours, but has some issues or needs further improvements during night shift. So when I compare here the travel times from my chosen ego vehicles, they fit pretty well. So SUMO fits pretty well the MATSim travel time, but of course for the off-peak hour, the SUMO ego vehicles are too fast. And if you wonder why the MATSim Lastgang is so flat, this is actually owed to the VSP adjustments by reducing the speed limit by 50%. MATSim is actually never able to attain a 50% relative mean speed here. And I actually wondered which travel time here is actually more realistic. The travel time here in the MATSim, in the travel time calibrated MATSim model, or is it more realistic in SUMO? And when I compared several ego vehicles with Google Street Map or with Google, actually they fitted more with MATSim. So the ego vehicles in SUMO, they're a little bit too fast. But this could be my fault, because I had, even during night hour, I had the actuated traffic lights on. So my guess is that I paved all the ego vehicles kind of a green wave. And perhaps it would be better to switch off the traffic lights at night, so that the ego vehicles are forced to stop in front of an intersection. And yeah. So conclusion. In this contribution, I introduced a two-step approach to calibrate network states on a spatio-temporally level. And this allowed me to align the traffic states in both MATSim and SUMO, or it allowed me to align the traffic states in SUMO to the MATSim traffic states. I identified measures that allowed me to maximize the throughput in the SUMO network, and I also performed a large parameter study to explore the robustness of these measures. And in the end, I applied a genetic algorithm that found me a more optimized numerical solution to align both traffic states. So all in all, I'm making good progress for my sequential MATSim SUMO tool coupling, but especially here with the calibration approach, I need further improvements here, especially during the night times. So that's it for me. Thank you very much.